Now that we have a handle on finding general solutions to homogeneous linear constant coefficient differential equations, let's throw away the homogeneous assumption and come back to trying to find solutions to non-homogeneous equations. Now, we saw that in general, if you have a non-homogeneous equation, all you need to do to find the general solution is find a particular solution for your non-homogeneous equation, that is, find a single solution to the equation, find the general solution to the associated homogeneous equation, and then just put them, just add them in this way. So we already know how to find if the associated homogeneous equation is a constant coefficient equation. We know how to find y sub c, that's the complementary solution it's called. So really we just need to figure out how to find one example of some solution to a differential equation of this type. So exactly how we find such a solution really depends on what the equation is, and especially what this inhomogeneous term on the right looks like. So let's look at an example. So we're going to try the second derivative of y minus 2 times first derivative of y minus 3y equals minus 3x plus 2. And what we're going to do is basically just guess, use black here, guess what we might use for a particular solution. Now, you can't just guess anything, because if you guess wrong, you won't find a solution. So what we'll need to do to make a good guess is imagine what happens to this guess for our particular solution when we put it into this differential equation. Well, what would happen to this function y sub p is it's going to get two derivatives, and then one derivative, and then no derivatives, and they're all going to be added together in various ways. And what this equation is saying is that what you should get when you combine all those derivatives is a polynomial. We should get minus 3x plus 2. So what's going to happen to this when we plug it in is it's going to get a few derivatives, they're going to be added up, and you're going to get a polynomial, a degree 1 polynomial. So what sorts of things, when you take derivatives and add them together, give you polynomials? Well, other polynomials. So what we should probably guess here is a polynomial. So what degree of polynomial? Well, whatever degree, say degree n, m, if we guess a degree m polynomial, then this y right here is going to be degree m. This derivative right here, dy dx, is going to be degree m minus 1, because when you take the derivative of a degree m polynomial, you get a degree m minus 1 polynomial. And the second derivative here is going to be degree m minus 2. On the right-hand side, we have degree 1. So when you add up the polynomials on the left-hand side, you're going to get degree m, because the largest degree is the function y. But we're supposed to get degree 1, so I guess that means m should probably be 1. So right here, we're going to guess a degree 1 polynomial. But we don't know which degree 1 polynomial. That's the whole problem. So we should guess a general degree 1 polynomial. In other words, we're going to have some undetermined coefficients that we need to figure out somehow. So maybe something like a times x plus b. Right, a degree 1 polynomial will have an x term, but we don't know the coefficient, and it will have a constant term, but we don't know the coefficient. So that's our guess for y sub p. Now, having these undetermined coefficients is what gives this whole trick its name. This is called the method of undetermined coefficients. one of the few cases in math where the name actually makes perfect sense. All right, so all we need to do to find a particular solution is figure out what these coefficients are supposed to be. And we have some information about y sub p. Y sub p is supposed to be a solution to the differential equation. So we can just plug y sub p into this differential equation. Of course, to do that, we need to take a couple derivatives. So y sub p prime is just a, y sub p double prime is 0, and now we can plug everything into the differential equation. So second derivative of y is 0, minus 2 times the first derivative of y, which is just a, minus 3 times y itself, so y sub p, which is ax plus b. And this is supposed to be equal to minus 3x plus 2. Okay, now things might look grim at first because we have one equation but two unknowns, two unknown coefficients, a and b. But in fact, we have as many equations as we need because this equation is supposed to be true for every value of x. So this single equation will let us determine all of the coefficients that we end up with. Okay, so there are a few different ways to actually find these coefficients. Let's start by just multiplying everything out and gathering up terms that have the same power of x. So let's see, we have only one term with x to the first power, that's right here. So that's minus 3ax. And then we have two terms that have no power of x. So there's minus 2a, and then right here there's minus 3b. Now this is supposed to be equal to minus 3x plus 2. So we can just compare coefficients, right? Both sides of this equation are polynomials, and if these are both polynomials that are equal, then their coefficients have to be equal. So that means minus 3a had better be equal to minus 3. And that tells us that a is 1. And then looking at the constant terms, minus 2a minus 3b had better be plus 2. Of course, we already know a at this point. A is 1, so minus 2 minus 3b equals 2. So minus 3b is 4, and so b is minus 4 over 3. And now that we know a and b, we know our particular solution. Our particular solution was ax plus b, but we just found a and b. So a is 1, so 1 times x is x, plus b, which is negative 4/3. So there's our particular solution. Now, to finish writing a general solution for the differential equation, we have to find the complementary solution as well. So let's do that. This is a constant coefficient differential equation. So let's write down the associated homogeneous equation. So y double prime minus 2y prime minus 3y. Okay, now we can write the characteristic equation, which is m squared minus 2m minus 3 equals 0. So, solve this. So this one factors. This is m minus 2 times, no, m minus 3 times m plus 1. And so m can be 3 and minus 1. So our complementary solution is some constant times e to the 3x plus some other constant times e to the minus x. And now we can put the particular solution and the complementary solution together. So our general solution to the original non-homogeneous differential equation is the particular solution, which was x minus 4/3. Yes, x minus 4/3. Plus our complementary solution, which was c1e to the 3x plus c2e to the minus x. And there we go. So as in a few previous cases in differential equations, really it came down to thinking a little bit about how we could make a good guess, but leaving enough freedom in our guess with the undetermined coefficients to lock down exactly what those coefficients are supposed to be.